This lesson is for FST Lesson 7.1 on polynomials. The word polynomials comes from the word poly and then nomials. Poly means many, nomials means terms. So if you're working with a polynomial, typically it'll have many terms. Keep in mind that polynomials do not have any sort of negative exponents. There'll be a combination of both baby calc and graphing calc questions in this lesson. We begin with a bunch of vocabulary that students can either copy from here or look in their book on page 438. Whenever you're working with a constant, that is simply a number without a variable. So if we're looking at this example here, the 1 here is the constant because it doesn't have a variable next to it. Same thing with the other example here, 7 is the constant. Whenever you're working with a polynomial, it's assumed that you know to write the polynomial in standard form. Standard form means you put the term with the highest exponent first and then all the other terms in descending order after that. Both of my examples here are written in standard form. Highest exponent is first, then any other numbers go in descending order after that. Same thing here, highest exponent is a 3. This one has an exponent of 1, so we go 3, 1, and then nothing, so that's in standard form as well. Next, let's jump to degree. We'll come back to monomial later. Degree is the highest exponent. So in this one, we'd say the degree is 5. Here, we'd say the degree is 3. Keep in mind that if you put it in standard form, usually the degree is really easy to identify. The leading coefficient is one that I want students to star. Leading coefficient can be confused with degree. Degree is the highest exponent. Leading coefficient is not referring to a high anything. The leading coefficient simply means, first of all, a coefficient on any variable is the number sitting in front of it. So the leading coefficient is the one that's in front or at the beginning after it's been put into standard form. So again, if both of these examples have been put in standard form, the leading coefficient is simply the coefficient that's at the beginning or in front. So in our first example here, the leading coefficient is 2. Notice that 3 is a higher coefficient, and that's not the one we're looking for. We're looking for the one in that very first position. So 2 is the leading coefficient of this one. This one doesn't have a coefficient, so remember when there is no number listed, it's an invisible 1. So this one has a leading coefficient of 1, this one has a leading coefficient of 2. Next, let's look at monomial, binomial, trinomial. Monomial, binomial, trinomial is a way to name the polynomial based on how many terms it has. Monomial is 1, binomial is 2, trinomial is 3. So if you look at this example here, the first one, it's a 2-term or a binomial polynomial. This one has 1, 2, 3 terms, so that's a trinomial. If you end up with a polynomial with 4 or more terms, there are no fancy names for those. You just say polynomial with 4 terms, polynomial with 5 terms, and so on. So one way you could name it is based on how many terms it has. Another way to name it is with the next 4 words: quadratic, quintic, cubic, or quartic. Quadratic refers to any polynomial of degree 2, so that would mean the highest exponent in that polynomial would be a 2. We call that a quadratic. Please don't confuse that with a quartic. Quartic looks an awful lot like a quadratic, but they are different degrees. Quartic is degree 4. To help you remember that, quart is kind of short for quarter, 4 quarters in a dollar. Cubic, I'm sure students are familiar with, that's to the power of 3 with the highest exponent of 3. Quintic is degree 5. There may be other special words that you'd use for degree 6 or degree 7 or degree 8, but I don't need students to know those for this course. So these are the only ones you would need to know. So let's name the 2 examples that we have here. This first one was x to the 5th plus 1. That is a, because of the degree, quintic, and because it's got 2 terms, binomial. And then you'd say with a leading coefficient, which I'll just abbreviate here, LC, with a leading coefficient of 1. Do the same thing here on our second example. It's a cubic, because the highest exponent is a 3, trinomial because it's got 3 terms, and we already said the leading coefficient is 2. So that would be the best way to name those. Try to name it by the degree, name it by how many terms it has, and then mention the leading coefficient. So students will have practice with that in the homework. Next, we're going to look at some volume word problems, because this is where polynomials play into real-life applications. First of all, when you're dealing with volume, remember that that's length times width times height. You need 3 dimensions in order to talk about volume. If you take or imagine a flat piece of paper or a flat piece of cardboard, someone has cut the corners out of it, and then they're going to fold it along those cut marks so that a box is formed. And so what you'll see is that if you actually did that with a piece of paper, you could fold up the sides and a box shape would result. So this edge would need to be attached. So these two would come together to form this edge. These two would form together to form this edge. This one goes back here. This one goes back here. So if we talk about x being the amount that's cut, then if we look at the dimensions, the vertical length here from top to bottom is supposed to be 10, but I cut an x off the bottom and I cut an x off the top. So that dimension on the side here is going to be 10 minus those two x's. So we took away an x from either side. We do the same thing with the other dimension. It was 15, but we took an x off of both ends. Be careful now, that's length and width, we still need a height. When you fold it, the height becomes the amount that you cut. So we're going to put x on the end. Students typically get stuck here and struggle with what to do with the x. Do you distribute it to the green, or do you distribute it to the purple, or do you distribute it to both? Rather than tackling that question and potentially getting it wrong, it's easier just to focus on the order of operations. You have 3 things to deal with here. 2 of them are in parentheses, so do those first. So go ahead and do FOIL here. When you're all done, distribute the x. Make sure you also put your final answer in standard form, highest exponent first and then in descending order after that. Typical mistake here is kids do the FOIL and then they quit. They also forget sometimes to add the like terms and they forget to write it in standard form. Those pieces are always assumed on polynomial questions. Make sure you've done 3 dimensions as well. The first 2 we did, then multiply by the x, and then put it in standard form. Let's quickly practice what we would name this polynomial. It's a cubic trinomial with a leading coefficient of 4. So you would be allowed to use a baby calculator only on this one. If you move on to volume, what is the maximum volume a box of this size could hold? This one you would be allowed to use a graphing calculator for. I've already done this on my graphing calculator, so I'm just going to show you the results that I got. First of all, I typed in that polynomial into a graphing page on my calculator. I had to modify the window a little bit because I couldn't see the full graph. So I had to play around with the numbers. You can see what I ended up arriving at. The x's went from -5 to 20. Originally it was -10 to 10, so I had to expand it a little bit. The y value, I ended up going from -50 to 200. When I graphed it, I think it went from like -6 to 6, and so clearly I could see that the graph was increasing up above what I could see, so I played around with what would be the best number there. Then if you look at the outcome, we got this kind of squiggly shaped graph, and I'm only going to worry about this portion here, because once we get to this point, my x is going to be negative, and I wouldn't be cutting a negative amount from the corner. That just wouldn't make sense. So I'm going to ignore the portion below the x-axis and anything past that. So I'm only going to worry about this portion here, so I'm going to look for the highest point that that section gets to. And we're going to give that type of situation a name when we go to the next item on our notes. So a quick reminder on how the calculator can help you get to that maximum point. So I'm just going to pull up my calculator momentarily. So I went ahead and graphed it, and now to get the calculator to identify this particular point, you can do menu trace, but I'm going to show you a little bit more reliable method. If you do menu, analyze graph, you'll notice that you have lots of choices. Minimum might be something you'd want to find, or possibly a 0. Today on this question we're looking for the maximum. Notice that it's asking me for a lower bound, so I want to go somewhere to the left of the point that I'm trying to identify. So I can click anywhere over here. When I click there, now it's going to ask me to find the upper bound, something to the right of the point that I'm trying to find. Make sure you don't go too far, because then it might get confused. Just notice the maximum does keep going there. So make sure you're not going too far. So I'm going to go to the right, and I can see there that that's my coordinate. So the coordinate that I got was 1.96 for x and 132 for y. So remember that the x represents how much we're cutting out of the corner. It also represents the height of the box. So we'd round that up to about 2 and say that 2 is what is cut from the corners. and then 132 is the maximum volume. So I wouldn't expect you guys to figure that out any other way than by using a graph on your graphing calculator. So the maximum volume, if you cut 2 from the corners, is 132. Obviously we're missing the units there. We'd have to give centimeters or inches or feet or whatever. Because it's volume, we'd say centimeters cubed or inches cubed. So it's a real-life application of how a polynomial could help you solve for a particular item. Because this isn't the maximum of the entire graph, it's just a maximum, we're going to give that type of situation a name called extrema. Extrema is when you're looking for the mins and the maxes on a graph. And also, a new item for you are the relative mins and maxes, also sometimes called local min or local max. So if you look at this first graph, similar to what we just dealt with on our volume question, this point here is supposed to be labeled B. Sorry, it's not very clear. Point B is a maximum point, but it's not the highest point of the graph because the graph does continue above it. So we would call this a local or relative max. Relative maxes might be things that we need to identify, just like on the previous question. This is a local max because the graph continues above it, but that's the one we need. So that's why we still identify it as a maximum, just a relative one. Similarly for A, the graph continues below it, but it's still a relative min or local min. Know that they don't always have to come in pairs. If you have one, that doesn't necessarily mean you're going to have the other. So if you look at the next graph, C is a minimum. The graph doesn't go anywhere below C, but there are 2 relative mins or local mins. E and G there are both minimum points that we might need to identify. Notice that D and F are maximums, but they are only local maxes. A local max just means there is a high point even though the graph continues above both of those. Keep in mind that when you have a minimum, you can also refer to that as a relative minimum, but when it becomes the minimum for the graph, then that label kind of takes priority. So notice this graph has a minimum but no maximum, and so those don't always have to be paired that way. On the third graph here, we have point H, and that point is simply the maximum point. Could also call it a relative max, but it is indeed the maximum, so that would be the only label that would be required. There is no minimum because the graph continues down forever. So again, here we could have called these upper ones relative maxes. These 2 down here could have been local mins. The last graph here has nothing for us to label. It's just increasing forever. There is a point right here that you'll maybe study when you get into calculus. That point is called an inflection point, where the concavity of the graph changes from concave up to concave down. But that is not something that we'll cover in FST. That would be more of a calculus situation. So that's called an inflection point for those of you moving on to calculus. Increasing and decreasing intervals are a very important part of this lesson, and they will show up on tests and quizzes. It's important here that students pay attention to the color because the color will enhance your understanding of increasing and decreasing intervals. It's also important for students to have an extra pen or pencil that they can use to drag across the graph vertically as a visual reference. So take a vertical pen or pencil, drag it across from left to right. That'll assist you with identifying the intervals. Keep in mind that arrows should be ignored here. So I should have said ignore there. Ignore arrows because the arrows can be misleading. Also, always read the graph from left to right. If you can keep those 2 things in mind, you'll be much more successful when it comes to intervals. So take your pencil and start dragging it slowly across your paper vertically, or across the screen. You'll see that this line, as you travel from left to right, is going up. And it's going up until it hits the blue section. So the line's increasing up until this point, then it starts to decrease. Then it goes up again. So the pink areas here are shaded that way because those are the increasing intervals on this graph. So we would describe them as starting at negative infinity, starting down here forever, and increasing until the x value becomes negative 1.3. It's also increasing in this section of the graph, starting at 1.3 for x, and then it goes up forever. So we'd say and 1.3 to positive infinity. If you were doing this on a test or a quiz and you only gave one of the two answers, you could potentially get only partial credit or no credit. When there are multiple intervals, you need to give all of them completely. As you drag your pencil from left to right, just in the blue section, if you drag it vertically, you're going to see that the line here to here is decreasing or going down. So the decreasing interval here is from negative 1.3 to 1.3. Keep in mind here that when you're doing intervals, you're giving your answers for the x values. Sometimes they don't give you values though, they don't have numbers listed, so we're going to use letters to help us describe the positive interval. Positive intervals are going to be dividing the graph horizontally. The increasing decrease divides them vertically. So a positive interval is anything above the x-axis. So if you look at the graph now and cover up the bottom part of it, ignoring the bottom of it completely, it's clearly above the x-axis in between these 2 points and from here up. So let's label those points with A, B, and C. So from A to B it's a positive, and from C to forever it's also positive or above the x-axis. So we just need to label that. So we're just going to say from A to B and from C to infinity. Be careful here, they may try to trick you by putting a coordinate here and calling it D. You would not say C to D here because the graph continues even above point D. So if they don't give you coordinates to locate different points on the graph, you can label them however you choose and then just refer to those to describe your intervals. Students need to practice those very much in the homework in order to be successful on these on tests and quizzes. Our final topic is on zeros. Another word for a zero is an x-intercept. I'm pretty sure students are familiar with x-intercepts on a graph. Make sure you identify all of them. This particular graph has 3. The first one's pretty easy to notice. It's at -2. The next one you might have to estimate a little bit, which means I'll allow some leeway on your answer. So if you said about -0.5 there, that would be perfectly acceptable. If someone else wrote -0.4, I'd probably still accept that. Be careful here, a lot of times kids will make careless mistakes here and put a -1.5 by mistake, so make sure you're counting carefully. This third one here, I would be careful here and say 2.5 is probably not where it's at because it's definitely not directly in the center, so I'd probably allow an answer like 2.3 or 2.4 there. So there's 3 zeros because it crosses the x-axis 3 times. Now pretend that the graph isn't there. Pretend we didn't know what the shape of the graph was. You also need to be able to identify zeros from a table alone. So the first one, hopefully that's standing out already because it's red. Whenever the y value is 0, that means this coordinate is sitting on the x-axis. So this is a 0 for sure. So look for zeros in the y to give you the x-intercept. So that can be a little bit misleading. Sometimes people think that where the 0 is for x, that's their answer, but it's the other way around. When you're sitting on the y-axis, the y value is 0 and you're looking for that x value. Now the other 2 zeros aren't as easy to identify. You want to look for changes from positive to negative or from negative to positive. Whenever that's happening, you must be crossing the x-axis in order to get from positive to negative or vice versa. So that's why it says look for those changes. There must be a 0 in between these numbers. So for listing out your answer from the table here, I would allow you just to say there's a 0 at -2, there's a 0 in between these 2 numbers, and there's another 0 in between these 2 numbers. And that would be sufficient for identifying where the zeros occur.